And moving on to another part of the world, Zhang is going to talk to us on the laboratory research on the laws of iron 3 clogging during urban stormwater and groundwater recharge.
Hello everyone, my name is Zhang Hexuan from Jilin University, China, and today I will talk about laboratory research on the loss of iron 3 clogging during urban stormwater groundwater recharge. Heavy metals have become an important part of stormwater pollutants, and they are usually absorbed and complexed and deposited in the water system. Among those heavy metal pollutants, iron is a common one. Iron in water, World Health Organization guidelines for drinking water quality value is 0.3 milligram per liter. But we can see, except for the extremely special condition of India, the content of iron in urban stormwater is usually 0.3 to 5 milligram per liter, and most of them are concentrated in the range of 0.3 to 1 milligram per liter. And according to the quality of the stormwater, we set up the indoor recharge experiment under the condition of 3 inlet iron concentrations and 3 infiltration medium and 3 infiltration velocity. And we analyzed the law and mechanism of iron clogging. The variation of permeability is obtained by using Darcy formula, and the sedimentary law of iron is obtained by mass ratio. The recharge experimental device is divided into 4 parts: water supply, Zumling collection, seepage column, and measuring pressure. Because the pH of urban stormwater is usually in the range of 7 to 8, so in this experiment we use ammonia to adjust the pH value of recharge solution to 7. And for results, we have 3 parts. First is hydraulic conductivity changes. The hydraulic conductivity changes were calculated as the permeability ratio, and we divided it into 3 parts. T1 is the permeability maintenance stage, and T2 is the permeability rapid decline, and T3 is the permeability slow decline or stable stage. And we can see, except in addition to E3, the different infiltration medium and infiltration the inlet concentration, the T1 is usually about 20 hours, and for high the course, after 80 hours, the final permeability value is about 80% of initial value. And for different inlet concentration, the medium concentration is about 20% of the initial value, and the low concentration about 40% of the initial value. For the finer sand and high infiltration inlet concentration is about it's over 90% of the initial value. And for the higher infiltration velocity, it's only need 35 hours the final permeability value of the initial value. And permeability decrease for the column inlet is similar to the whole column changes. In the remaining part of the column, the change of hydraulic conductivity is slower and over much more smaller range. Therefore, hydraulic conductivity changes mostly occurred in the inlet. The mass deposit distribution was also obtained by dismantling of the column at the end of the experiment. Most iron was deposited within 0 to 1 centimeter from inlet, and the higher infiltration velocity have a higher mass deposition rate. For all experiments, in addition to coarse sand, over 80% iron was deposited on column, and for higher infiltration velocity, concentration, and finer sand, there are over 90% iron deposited on 0 to 1 centimeter, and they also have the higher mass disposition rate. High infiltration velocity have the highest mass deposition rate, which is 0.47 milligram per hour. And for different infiltration medium, iron is concentrated on the inlet, this part, and so this part's color looks more darker. Coarse sand and medium sand column become yellow at the end of the experiment, but fine sand looks like pure white over 2 centimeters. According to the experimental phenomena and the clogging law, we think the clogging mechanism has adsorption and filtered interception. Iron will become iron hydroxide dissipated at a pH value greater than 3. So when we use the recharge solution with pH is 7, iron in the recharged water is about iron hydroxide particles with the diameter about 1 micron. And the ISMAR picture of recharged water shows higher inlet concentration increasing the number of iron hydroxide particles as well their diameter. We can see the different infiltration medium ISMAR picture, which is at the end of the experiment from column inlet and outlet. The coarse sand and the finer sand was covered with iron hydroxide is much more than the core sand, and for outlights, the core sand exhibit a little iron hydroxide particles, but the finer sand outlight it looks like doesn't have. When we use surface clogging model to simulate all fine sand experiments hydraulic conductivity changes, the relative coefficient over 0.95. So we know fine sand clogging mechanism is surface filtered interception. All the adsorption experiment fitted pseudo second order kinetic equation. It means the adsorption is almost chemical adsorption and fitted Friend-Lange equation and constant less than 0.5. It means the adsorption is not easy to happen. So, according to the phenomena of clogging and simulate, we can get some conclusion. First, iron clogging usually occurs on the surface of infiltration medium. The occurrence time, the depth, and the degree of clogging are all affected by the size of infiltration medium, the infiltration concentration, and the infiltration velocity. Second, iron mostly remained near the surface of infiltration medium, and its retention rate and retention quantity were affected by the size of infiltration medium and the inlet concentration and the infiltration velocity. Finally, the mean mechanism of iron clogging can be concluded as filtration, and the substance causing the clogging is iron hydroxide particles. And we have other clogging models such as insect clogging and mixed clogging is building. And if you want to have some connection with China and or Jilin University, you can send emails to this to address. Thank you.
Thanks very much, Zhang. Are there any questions for Zhang in relation to some of her experimental results?
Thank you for presenting the results of this unique experiment. I was wondering, why did you choose for ammonium for your pH buffering, as you run the risk of biological clogging and potentially also the reducing of your iron hydroxides?
I use ammonia, right?
Yeah. Why did you use ammonia for your ammonium for your pH buffering?
Because ammonia, it doesn't have any heavy metal. If I use some others to make the pH to 7, it must have the heavy metal. So the clogging is not. So the clogging is not just about iron; it's about something else,
Okay.
like some else metal, heavy metal.
Thank you.
One other question.
In one of your first tables, you showed really high concentrations of iron. So these are real measured concentrations in urban stormwater. So I was really surprised by these high levels. And do they occur as suspended iron flocks, or is this still ferrous iron 2? Do you know something about this? So the iron that gets into a filter system, is that suspended iron 3, iron flocks, or still iron 2?
Sorry? This
Yeah,
picture?
this one.
Oh, okay. The iron in this picture is some from the articles and some from our we test.
It's the urban stormwater where it was measured.
It's just storm water. It's the rainwater.
You have any idea why it can get that high?
Yeah.
Like up to 40 milligrams per liter in India? Was there a specific reason for that?
The India is from paper I saw.
Right, okay.
I can
Special
comment a
conditions.
little bit on the Australian examples up there in relation to the iron, and it's not unusual for us to see, 2 milligrams per litre up to 15 milligrams per litre. It's typically iron 2. We've just recently, over the last couple of years, seen a spike in the iron concentrations in the urban stormwater runoff, as well as the aluminium concentrations associated with a change in pH of the stormwaters coming off in relation to the very, very dry conditions that we've had recently. And then, of course, as soon as we've had some really good heavy rains, the whole system has increased in those sorts of concentrations. But it is mostly iron 2.
It could also be leakage of sewage, effluent in the system.
Yeah. We certainly not. We hope not at least in the Adelaide ones, because we do a lot of checking for sewer leaks. But sewer overflows and sewer leaks is a risk in an urban stormwater harvesting environment. Yeah. Okay. No more questions. Thanks very much, Zhang.
Thank you.